huge the expanding universe and those resources you sent over. Really fascinating stuff.
Oh, definitely. We've got a good mix, haven't we? There's that general overview text, then that arcs of style piece, almost like a theoretical sketch, and of course, insights from Peebles' big book, Principles of Physical Cosmology.
Yeah,
Can't ignore Peebles.
exactly. And the question that's really been buzzing around in my head, and I bet yours too, is this. Okay, space is stretching, right? Continuously. And we know the speed of light is constant, unchanging. So does that mean light, as it travels through this stretching space, somehow ends up covering more distance in the same amount of time? It just feels weird, like a cosmic puzzle.
It absolutely is. It's one of those wonderfully counterintuitive things about cosmology.
Yeah.
And yeah, that's our mission today, isn't it? To sort of dive into that seeming contradiction.
Right.
To figure out how cosmic expansion and that constant light speed actually work together and, what it reveals about everything. Hopefully we can unlock a few of those aha moments for you, our listener.
Okay, perfect. Let's get into it. So this cosmic expansion, Hubble's law, keeps coming up. What's the core idea there, basically?
Right. Hubble's law. At its heart, it's the observation that galaxies are moving away from us. And the key part, the farther away a galaxy is, the faster it appears to be receding.
Ah, okay. Faster if it's further.
Exactly. It's a direct proportionality. And we quantify that rate with the Hubble constant, HOS. This isn't just showing the universe is growing. It lets us, trace things back, way back to the early universe.
So it's getting bigger. We can measure how fast. And that measurement tells us about its history.
Precisely. And it's really important to remember, and we're talking big picture here, like vast cosmic scales, the whole distribution of galaxies, this expansion, looks pretty much uniform. Space stretching evenly in all directions, kind of. No special center point.
Okay, uniform on the grand scale. But then, didn't one of the sources mention it's not quite so neat and tidy everywhere, like locally?
Yes, that's a crucial bit of detail. While the overall trend is uniform expansion on those huge scales, gravity really messes with things locally.
Right, gravity.
So in places where there's a lot of matter packed together, think of our own local group with the Milky Way and Andromeda.
Yeah, we're actually moving towards Andromeda, aren't we?
Exactly. The gravitational pull between galaxies like ours is strong enough to overcome the cosmic expansion in that region. So they aren't flying apart like Hubble's law alone might suggest. Gravity holds them together.
Okay, that makes sense. Gravity wins locally. And the source also said something about cosmic voids expanding faster.
Yep, that's the flip side. In those enormous, relatively empty patches between galaxy clusters, the voids, there's much less stuff, so much less gravity pulling things together.
Less resistance, maybe.
Kind of. So in those voids, the expansion can actually happen at a rate that's, well, faster than in the denser areas.
Huh. So the universe is sort of, I don't know, patchy or bubbly in how it expands. It's fascinating. And this leads into anisotropy, dark energy.
Yeah.
Sounds like we're getting into the big unknowns.
We definitely are touching upon the frontiers here. The text source rightly points out that, the very early universe, super uniform expansion, we see that in the cosmic microwave background. But today, we're still trying to nail down if the expansion is perfectly the same in every direction. And then there's dark energy, making the expansion accelerate.
Which complicates things further.
Hugely. If dark energy itself isn't perfectly smooth everywhere, maybe it causes tiny differences in the expansion rate depending on which way you look. That's this anisotropy idea. It's a very active area of research right now.
Okay, so we've got this picture. Overall expansion, but with local gravity holding things back and voids maybe expanding faster, plus this accelerating mystery driver. Got it. Now, the other piece of the puzzle, the speed of light, constant. That's Einstein, right?
Absolutely. Special Relativity 101. The speed of light in a vacuum, see, is, well, a universal constant, about 300,000 kilometers per second. Doesn't matter if you're moving or the light source is moving. It's always the same. A bedrock principle.
Always the same. Okay, so back to the core question, the one you posed so well. If space itself is stretching, how does light traveling through it not, effectively cover more distance in the same time? Doesn't that break the constant speed rule?
That is the crux of it, isn't it? And the key is realizing that the light speed locally, like right where the photon is, at any given instant is constant. It's always c.
Okay.
But it's the space between things that's expanding. The fabric of space-time itself is stretching. The light isn't suddenly finding a faster gear or a shortcut within a static grid. The grid itself is growing.
Okay, that analogy from the Arcova style piece, the rubber band. Can you walk us through that again? Help me.
Sure. Imagine drawing dots, say galaxies, on a rubber band. Now, stretch the band.
The dots move apart.
Right. The distance between any two dots increases. But the dots themselves aren't like scrambling along the rubber faster than before. They're just being carried apart because the rubber itself is stretching.
Okay.
It's similar with the universe. Galaxies generally aren't speeding through space faster than light because of the expansion. It's the space between them that's doing the stretching, carrying them along.
So they're basically riding the wave of expanding space.
That's a great way to put it, yeah. And now the really cool part is what this stretching space does to the light traveling through it.
Right. Redshift, that came up a lot. Cosmological redshift, how does that fit in?
Exactly. So as light travels these immense distances across space that is actively stretching, the light wave itself gets stretched out along with the space.
Like the wave on the stretching rubber band.
Precisely. If you stretch the rubber band while a wave is traveling along it, the wave gets longer. For light, a longer wavelength means it shifts towards the red end of the spectrum, hence cosmological redshift.
So it's not that the light is like getting tired and slowing down. Its fundamental speed is the same, but the space it's in is changing its wavelength.
You've got it. The photon's local speed is always c. But because the space it traveled through stretched during its journey, its wavelength got longer. And crucially, as one of the sources noted, a bigger cosmological redshift does mean the light traveled through more stretched space. So in the context of this expanding universe, you could say it effectively covered a greater physical distance due to all that cumulative stretching over time.
Okay, that's starting to click. But the sources warned about confusing this with other redshifts.
Yes, very important distinction. There's Doppler redshift that's just from things moving away from us through space, like an ambulance siren changing pitch.
Standard Doppler effect.
Right. And gravitational redshift, that's light losing energy climbing out of a gravity well. Both shift light redward, but they don't inherently tell you about the large-scale stretching of space-time itself like cosmological redshift does.
Got it. So cosmological redshift is our specific fingerprint for light that's journeyed across expanding space. Now, Peebles, foundational figure, you said, what does his book add to this?
Right. Peebles' Principles of Physical Cosmology. It provides the rigorous mathematical underpinning. He lays out how cosmologists model the expanding universe using something called the FLRW metric. That's the mathematical description of a universe that's broadly the same everywhere and in all directions.
FLRW metric, okay.
And central to that is the scale factor, usually written AT. Think of it like a cosmic zoom level that changes with time. If AT doubles, the distances between distant, free-floating objects also double.
And Peebles really hammers home that redshift comes from this stretching, this changing scale factor, not light-changing speed.
Absolutely. He's crystal clear. Cosmological redshift is a direct result of the scale factor increasing while the light is in transit. It stretches the wavelength. All the fundamental physics, including Constancy, holds true within this expanding framework.
Okay. He also talked about different ways to measure distance, didn't he? Proper distance and co-moving distance. How does that work?
Exactly. This can be a bit tricky, but it's key. Proper distance is, well, the actual physical distance between 2 points at one specific moment in time, like using a giant ruler right now.
If we could freeze time and measure.
Right. Co-moving distance, though, is clever. It factors out the overall expansion. Imagine our dots on the rubber band again. Even as the band stretches, the co-moving distance between the dots stays the same, measured in rubber band units, if you like.
It's like a coordinate system that stretches with the universe.
Pretty much. So a distant galaxy might have a constant co-moving distance from us, but its proper distance is constantly increasing as the universe expands. That's why light takes billions of years to get here. And Peebles emphasizes that photons, always moving locally at sea, end up crossing larger and larger proper distances because the universe expands during their trip.
And this connects to the particle horizon idea. That came up too. Peebles covers that.
Yes, he does. The particle horizon, as Peebles explains it, is basically the maximum co-moving distance from which light has had time to reach us since the Big Bang. Anything further away, light just hasn't had enough cosmic time to complete the journey, given the expansion.
So the fact we see things near that horizon.
Means that light has made an incredibly long journey, a journey made even longer in terms of proper distance by all the expansion that happened along the way.
So in a sense, the expansion allows light to effectively bridge distances that would be impossible to cross in the same amount of cosmic time if the universe were static.
That's a perfect way to summarize it. Yes. The cumulative effect of expansion over billions of years creates these vast travel distances and observable effects like redshift and the horizon.
Wow. Okay. And just quickly looping back, that text mentioned dark energy and the accelerating expansion. How does that fit?
Right, the acceleration. It basically means the scale factor 8AT isn't just increasing, its rate of increase is also increasing. Dark energy is pushing things apart faster and faster.
So the stretching is speeding up.
Exactly. We don't fully get why yet. I mean, what dark energy is, but its effect means the stretching is accelerating. This definitely impacts the long-term future, the ultimate size of the observable universe, and so on. But the core principles we talked about, light's constant local speeds, space stretching the wavelength, those still apply.
Okay, let's try and wrap this up for everyone listening. So the big takeaway seems to be light always travels at the same speed locally, always c.
Mm-hmm.
But the universe itself isn't static. Space is expanding, stretching like that rubber band. This stretching increases the proper distance between things and crucially stretches the wavelengths of light traveling through it.
Yep, causing cosmological redshift.
Right. So light from far away has journeyed through more and more stretched space over cosmic time, meaning it's effectively crossed a greater distance than it would have in a static universe.
You've nailed it. The universe plays by these really interesting rules, constant light speed locally, but within a dynamically expanding stage. It's how these two ideas interplay that shapes what we see.
It really has been eye-opening. Okay, so maybe a final thought for you, listener, to chew on. We know the expansion is accelerating because of dark energy. So, what does that imply about the ultimate limits of what we can ever hope to see? As the expansion speeds up faster and faster, how might that affect the light trying to reach us from the most distant corners of the cosmos in the far, far future? Something to ponder about the ultimate fate and visibility of our universe.